Learning objectives. In this chapter, the user would learn the following in detail. Conventional aerial photography, small format aerial photography, chemistry of film exposure, the nature of light, the electromagnetic spectrum, rectilinear propagation, specular, diffuse and total reflection, reflection and absorption, wavelength and color, temperature. The human eye, morphology, rods and cones, acuity and circle of confusion, persistence of vision, parallax and perspective, photography versus the human eye. Film stock and processing, photochemical spectrum, structure and antihalation, speed and exposure, processing, densitometry, sensitometry, contrast control, gamma, controls of exposure, light meters and automatic cameras, color infrared film. Introduction to cinematography. Cinematography is a science or art of motion picture photography by recording light or other electromagnetic radiation, either electronically by means of an image sensor or chemically by means of a light-sensitive material such as film stock. Aerial photography. Aerial photography is the taking of photographs of the ground from an elevated position. Platforms for aerial photography include fixed-wing aircraft, helicopters, multi-rotor unmanned aircraft systems, UAS, balloons, blimps and dirigibles, rockets, kites, parachutes, standalone telescoping and vehicle-mounted poles. First aerial photography was taken from the height of 630 meters by French photographer and balloonist Gaspard Félix Tourneschon, known as Nader, in 1858 over Paris. Frenchman Arthur Batoud began using kites for photography in 1888. The use of aerial photography rapidly matured during the war as reconnaissance aircraft were outfitted with cameras to record enemy movements and defenses. Aerial photography is used in cartography, land use planning, archaeology, movie production, environmental studies, surveillance, commercial advertising, conveyancing, and artistic projects. Types of aerial photography. There are 4 types of aerial photography. They are oblique, vertical, combinations, orthophotos. Oblique photographs. Photographs taken at an angle are called oblique photographs. Vertical photographs. Vertical photographs are taken straight down. Comparison of oblique photographs. Combinations. Aerial photographs are often combined. For example, panoramas. Panoramas can be made by stitching several photographs taken with one handheld camera. Orthophotos. Photographs which have been geometrically corrected so as to be usable as a map. The conventional aerial photograph. Conventional aerial photographs contain image displacements, distortion caused by camera lens distortions, camera tip and tilt, terrain relief, and scale. The conventional aerial photograph has been the most common tool of the photogrammetrist in order to provide plane, metric, and topographic images. Conventional photography has been used with great efficiency for mapping the Earth, Moon, and the surfaces of other planets. Uses. It is used to take record shots, that is, photograph taken to purely record information. It is also used to take progress shots, for example, progress of a construction company. It is also used for clicking marketing shots. These images have to fulfill the marketing objectives, for example, marketing of a newly constructed building. Small format aerial photograph offers a relatively low cost and simple do-it-yourself alternative to obtain up-to-date aerial photo coverage. It is best suited for relatively small areas where no precision mapping is required. These photos are used as thematic information. Chemistry of film exposure. The name film originates from the fact that photographic film, also called film stock, has historically been the medium for recording and displaying motion pictures. Photographic film is a strip or sheet of transparent plastic film base coated on one side with a gelatin emulsion containing microscopically small light-sensitive silver halide crystals. The sizes and other characteristics of the crystals determine the sensitivity, contrast, and resolution of the film. The emulsion will gradually darken if left exposed to light, but the process is too slow and incomplete to be of any practical use. Instead, a very short exposure to the image formed by a camera lens is used to produce only a very slight chemical change proportional to the amount of light absorbed by each crystal. This creates an invisible latent image in the emulsion, which can be chemically developed into a fully visible photograph. In addition to visible light, all films are sensitive to X-rays and high-energy particles. The parts of the film have 4 layers: blue sensitive layer, green sensitive layer, red sensitive layer, clear film base. Color film uses at least 3 layers. Dyes, which adsorb to the surface of the silver salts, make the crystals insensitive to different colors. Typically, the blue sensitive layer is on top, followed by the green and red layers. The rays produce fluorescence on celluloid. The following are the properties of processing the film. Animation, the components of film. The active component of film is an emulsion of radiation-sensitive crystals coated onto a transparent base material. The production of an image requires 2 steps. First, the film is exposed to radiation, typically light, which activates the emulsion material but produces no visible change. The exposure creates a so-called latent image. Second, the exposed film is processed in a series of chemical solutions that convert the invisible latent image into an image that is visible as different optical densities or shades of gray. The darkness or density of the film increases as the exposure is increased. Development of film spectrum sensitivity. Many are at least slightly sensitive to invisible ultraviolet UV light. Some special-purpose films are sensitive to the infrared IR region of the spectrum. The cameras used are common off-the-shelf professional and good quality amateur cameras. Nature of light. The term light sometimes refers to electromagnetic radiation of any wavelength, whether visible or not. Electromagnetic spectrum sources. The most common light sources are thermal. A body at a given temperature emits a characteristic spectrum of black body radiation. A simple thermal source is sunlight. The radiation emitted by the chromosphere of the sun at around 6000 Kelvin peaks in the visible region of the electromagnetic spectrum when plotted in wavelength units, and roughly 44% of sunlight energy that reaches the ground is visible. Another example is incandescent light bulbs, which emit only around 10% of the energy as visible light and the remainder as infrared. Physicists at the Stanford Linear Accelerator Center, SLAC in California, have succeeded in producing particles of matter from very energetic collisions of light. The team, which included researchers from Stanford University, the University of Rochester, New York, the University of Tennessee in Knoxville, and Princeton University, New Jersey, published an account of their work in the September 1, 1997 issue of the journal Physical Review Letters. Scientists have long known that matter can be converted to energy, and conversely, energy can be converted to matter. In an atomic bomb blast, a very small amount of matter is converted to its equivalent in energy, creating an immense explosion. Scientists have also created matter from energy by bombarding heavy atoms made up of many protons and neutrons, with high-energy radiation in the form of X-rays. Collisions between X-ray beams and the atoms created matter in the form of set of electron and positron particles, a phenomenon known as pair production. Positrons are particles that have the same weight and amount of charge as electrons, but positrons are positively charged, while electrons are negatively charged. In the recent experiments at SLAC, physicists accelerated a beam of electrons to nearly the speed of light. Certain chemicals produce visible radiation by chemoluminescence. In living things, this process is called bioluminescence. For example, fireflies produce light by this means, and boats moving through water can disturb plankton, which produces a glowing wake. Certain substances produce light when they are illuminated by more energetic radiation, a process known as fluorescence. Some substances emit light slowly after excitation by more energetic radiation. This is known as phosphorescence. Rectilinear propagation. In a homogeneous transparent medium, light travels in a straight line, and this is known as rectilinear propagation of light. Specular. Specular reflection is a mirror-like reflection of light or of other kinds of wave from a surface in which light from a single incoming direction, a ray, is reflected into a single outgoing direction. Diffuse and total reflection. Diffuse reflection. The surface is not smooth, and the direction of the normal to the surface will vary from point to point. Again, normals at 3 different points are illustrated. While the entire incoming beam travels in the same direction, different regions of the beam will produce different angles of incidences due to the differing direction of the normals. For the leftmost region, indicated by a green label, the angle of incidence is 74 degrees. But the central purple labeled beam produces an angle of incidence of only 43 degrees. At each point, the law of reflection holds, so the different regions of the beam will reflect with equally diverse angles of reflection. Thus, the reflected light will scatter in all directions. This scattering of light upon reflection is called diffuse reflection. Total reflection. The surface is smooth, and the normal to the surface will point in the same direction at each point on the surface. The normals at 3 different points on the horizontal surface are indicated by the dashed vertical lines. As the beam strikes the surface, each region of the beam of light will produce the same angle of incidence. The same angle of incidence means the same angle of reflection, so the entire beam will reflect together with an angle of reflection equal to the angle of incidence. This uniform reflection is called total reflection. Refraction and absorption. Refraction of light. Refraction is a bending of light rays when passing through a surface between one transparent material and another. It is described by Snell's law. The phase velocity is important in determining how a light wave travels through a material or from one material to another. It is often represented in terms of a refractive index. Absorption of light. The light wave could be absorbed by the object, in which case its energy is converted to heat. The light wave could be reflected by the object, and the light wave could be transmitted by the object. Wavelength and the color pulse of light. A pulse of light or wave packet, a cluster made up of many separate interconnected waves of different frequencies, is drastically reconfigured as it passes through the vapor. Some of the component waves are stretched out, others compressed. Yet at the end of the chamber, they recombine and reinforce one another to form exactly the same shape as the original pulse. Wang said, "It's called refacing." Nature of anode rays. The key finding is that the reconstituted pulse reforms before the original intact pulse could have gotten there by simply traveling through empty space. That is, the peak of the pulse is, in effect, extended forward in time. As a result, detectors attached to the beginning and end of the vapor chamber show that the peak of the exiting pulse leaves the chamber about 62 billionths of a second before the peak of the initial pulse finishes going in. Frequency moves at a different speed in glass, smearing out the original light beam. Blue is slowed the most and thus deflected the farthest. Red travels fastest and is bent the least. That phenomenon produces the familiar rainbow spectrum. Light is measured with 2 main alternative sets of units. Radiometry consists of measurements of light power at all wavelengths, while photometry measures light with wavelength weighted with respect to a standardized model of human brightness perception. Temperature. Color temperature has been described most simply as a method of describing the color characteristics of light, usually either warm, yellowish, or cool, bluish, and measuring it in degrees of Kelvin, degree K. A more technical definition assigns a numerical value to the color emitted by a light source measured in degrees of Kelvin. The Kelvin color temperature scale imagines a black body object, such as a lamp filament, being heated. Light sources that are not incandescent radiators have what is referred to as a correlated color temperature, CCT. Its connotations to any part of the color temperature chart are strictly visually based. Lights with a correlated color temperature do not have an equal radiation at all wavelengths in their spectrum. In our scale, tungsten halogen has a color temperature of 3200 degree K. There are variations in these standards, but this is a good start to understanding the relationship between different colored light sources. Chadwick's experiment. Chadwick's experiment included projecting alpha particles toward beryllium, the light element. The emitted particles, after enduring the beryllium target, become neutrons and fall on the paraffin wax. The paraffin wax in turn releases another type of particle, protons. At that time, atoms were thought to be made up of protons and electrons. Charge to mass ratio. Charge on the electron. R.A. Millikan, 1868 to 1953, devised a method known as oil drop experiment, 1906 to 14, to determine the charge on the electrons. The human eye. The human eye belongs to a general group of eyes found in nature called camera-type eyes. Instead of film, the human eye focuses light onto a light-sensitive membrane called the retina. The human eye can distinguish about 10 million colors. Morphology of the human eye. Human eyes have a widely exposed white sclera surrounding the darker colored iris, making it easy to discern the direction in which they are looking. We compared the external morphology of primate eyes in nearly half of all primate species and showed that this features uniquely human. Humans have the largest ratio of exposed sclera in the eye outline, which itself is elongated horizontally. We suggest that these are adaptations to extend the visual field by allowing greater eye movement, especially in the horizontal direction, and to enhance the ease of detecting the gaze direction of another individual. Working of human eye. The cornea is a transparent structure found in the very front of the eye that helps to focus incoming light. Behind the cornea is a colored ring-shaped membrane called the iris. The iris has an adjustable circular opening called the pupil, which can expand or contract depending on the amount of light entering the eye. Rod and cone cells in the retina allow conscious light perception and vision, including color differentiation and the perception of depth. Dimensions of human eye. The dimensions differ among adults by only 1 or 2 millimeters. The vertical measure, generally less than the horizontal distance, is about 24 mm among adults. At birth, about 16 to 17 millimeters, about 0.65 inches. The eyeball grows rapidly, increasing to 22.5 to 23 millimeters, approximately 0.89 inches, by 3 years of age. By age 13, the eye attains its full size. The typical adult eye has an anterior to posterior diameter of 24 millimeters, a volume of 6 cubic centimeters, 0.4 cubic inches, and a mass of 7.5 grams, weight of 0.25 ounces. Components of human eye. The eye is made up of 3 coats enclosing 3 transparent structures. The outermost layer, known as the fibrous tunic, is composed of the cornea and sclera. The middle layer, known as the vascular tunic or the uvea, consists of the choroid, ciliary body, and the iris. The innermost is the retina, which gets its circulation from the vessels of the choroid as well as the retina vessels. Field of view. The approximate field of view of an individual human eye is 95 degrees away from the nose, 75 degrees downward, 60 degrees toward the nose, and 60 degrees upward, allowing humans to have an almost 180-degree forward-facing horizontal field of view. With eyeball rotation of about 90 degrees, horizontal field of view is as high as 270 degrees, about 12 to 15 degrees temporal, and 1.5 degrees below horizontal is the optic nerve or blind spot, which is roughly 7.5 degrees high and 5.5 degrees wide. Near response. The adjustment to close-range vision involves 3 processes to focus an image on the retina. They are vergence movement, pupil construction, accommodation of the lens. Vergence movement. When a creature with binocular vision looks at an object, the eyes must rotate around the vertical axis so that the projection of the image is in the center of the retina in both eyes. To look at an object closer by, the eyes rotate towards each other, convergence, while for an object farther away they rotate away from each other. Pupil constriction. Lenses cannot refract light rays at their edges as well as they can closer to the center. The image produced by any lens is therefore somewhat blurry around the edges. It can be minimized by screening out peripheral light rays and looking only at the better focused center. accommodation of the lens. To change the curvature of the lens, accommodation is carried out by the ciliary muscles surrounding the lens contracting. This narrows the diameter of the ciliary body, relaxes the fibers of the suspensory ligament, and allows the lens to relax into a more convex shape. Rods and cones of human eye. The retina is the back part of the eye that contains the cells that respond to light. These specialized cells are called photoreceptors. There are two types of photoreceptors in the retina, rods and cones. Rods and cones generate nerve impulses in the retinas of the eyes that travel along the optic nerves to the optic chiasma, where they partially cross over. The sensory organs for vision. The eyes are at the front of the head, but areas of the brain at the back and sides provide the actual visual sense. Rods of human eye. The rods are most sensitive to light and dark changes, shape and movement, and contain only one type of light-sensitive pigment. Rods are not good for color vision. In a dim room, however, we use mainly our rods, but we are colorblind. Rods are more numerous than cones in the periphery of the retina. Cones of human eye. The cones are not as sensitive to light as the rods. However, cones are most sensitive to one of three different colors, green, red, or blue. Signals from the cones are sent to the brain, which then translate these messages into the perception of color. There are about 6 million cones in the human retina. Acuity and circle confusion. Visual acuity of the human eye. Visual acuity, VA, is the acuteness or clearness of vision, which is dependent on optical and neural factors. That is, the sharpness of the retinal focus within the eye, the intactness and functioning of the retina, and the sensitivity of the interpretative faculty of the brain. Example for visual acuity. The case of a person with normal 20/20 vision can be considered. As light enters the eye through the pupil, it passes through the lens and is projected on the retina at the back of the eye. Circle of confusion. In optics, a circle of confusion is an optical spot caused by a cone of light rays from a lens not coming to a perfect focus when imaging a point source. It is also known as a disk of confusion, circle of indistinctness, blur circle, or blur spot. Circle of confusion in photography. In photography, the circle of confusion is used to determine the depth of field, the part of an image that is acceptably sharp. A standard value of circle of confusion is often associated with each image format, but the most appropriate value depends on visual acuity. Persistence of vision. Persistence of vision is a phenomenon of the eye by which an after image is thought to persist for approximately 1/25th of a second on the retina and believed to be the explanation for motion reception. However, it only explains why the black spaces that come between each real movie frame are not perceived. Theory of persistence of vision. The theory of persistence of vision is the belief that human perception of motion, brain-centered, is the result of persistence of vision, eye-centered. The theory was disproved in 1912 by Wertheimer, but persists in many citations in many classic and modern film theory texts. Parallax and perceptive parallax of human eye. Parallax is a displacement or difference in the apparent position of an object viewed along two different lines of sight and is measured by the angle or semi-angle of inclination between those two lines. The term is derived from the Greek parallaxis, meaning alteration. Perspective of human eye. Perspective, in the context of vision and visual perception, is a way in which objects appear to the eye based on their spatial attributes, or the dimensions and the position of the eye relative to the objects. There are two main meanings of the term, linear perspective and aerial perspective. Photography versus the human eye. Structurally, our eyes and cameras are very much alike. Similarities: light rays pass through a lens and are focused on a light-sensitive material. For digital cameras, this material is a semiconductor device. For our eyes, the material is a retina. Notice in the picture how both flip the object upside down. This is a result of light passing through a small hole. In the eye, this hole is a pupil. In the camera, the hole is called the aperture. For cameras, turning the object back upright isn't a problem. Just turn the resulting photo back upright. For eyes, the optic nerve carries the light signal to the brain, which automatically flips the image upright. Clever brain. For our eyes, this means what we really see is our mind's reconstruction of objects based on the input provided by the eyes, not the actual light received by our eyes. The difference is current digital cameras have 5 to 20 megapixels. The human eye is able to resolve the equivalent of a 52 megapixel camera. Photochemical spectrum. A photograph is an image made by a photochemical reaction which records the impression of light on a film surface coated with silver atoms. Photography utilizes this chemical principle to record color and black and white images. Silver salt chemistry remains the preferred method of recording high-quality images despite advances in electronic technologies and digital imaging. Structure and anti-halation structure. Film is made of a suspension of silver halide crystals in a gelatin binder. This emulsion is finely layered many times along with any dyes for color or processing agents onto a celluloid base, protected on the backside with physical handling coatings. The silver halide crystals are the actual photoreactive medium. Antihalation. An antihalation is a layer found in most photographic films. It is usually a coating on the back of the film base, but sometimes it is incorporated between the light-sensitive emulsion and the base. The light that passes through the emulsion is absorbed by the antihalation layer. Speed and exposure. In photography, shutter speed or exposure time is the length of time a camera shutter is open when taking a photograph. The amount of light that reaches the film or image sensor is proportional to the exposure time. Processing in film. Photographic processing is a chemical means by which a photographic film and paper is treated after photographic exposure to produce a negative or positive image. Photographic processing transforms the latent image into a visible image, makes this permanent and renders it insensitive to light. Densitometry. A densitometer measures light absorption due to the presence of colorant such as ink and toner. It mainly measures colorant amount and not color. Types of densitometry. Transmission and reflection densitometry. A transmission densitometer measures the amount of light passing through film or any other transparent medium. A reflection densitometer measures the light reflected from a surface, usually paper. Sensitometry. Sensitometry is the scientific study of light-sensitive materials, especially photographic film. The study has its origins in the work by Ferdinand Herter and Vero Charles Driffield, circa 1876, with early black and white emulsions. Purpose of sensitometry. Evaluation and maintenance of exposure factor systems, intensifying screens and monitoring of processing equipment. Contrast control. The contrast control is used to set the overall luminance of the display to the appropriate level. Another word for luminance is brightness, which is why it's confusing that the control that adjusts luminance is called contrast and not brightness. But those are the names the original video engineers gave the controls. Gamma is the name of a non-linear operation used to code and decode luminance or trisimulus values in video or still image systems. The effect of gamma correction on an image. The original image was taken to varying powers, showing that powers larger than 1 make the shadow darker, while powers smaller than 1 make the dark regions lighter. Controls of exposure. Exposure is controlled by 3 functions. Shutter speed, which determines the length of time you allow light into a camera. Aperture, which determines the size of the opening through which light enters the camera. ISO, which corresponds to the sensitivity of digital cameras' image sensor to light. Light meters and automatic cameras. Definition. A light meter is a device used to measure the amount of light. In photography, a light meter is often used to determine the proper exposure for a photograph. Typically, a light meter will include a computer, either digital or analog, which allows a photographer to determine which shutter speed and F number should be selected for an optimum exposure given a certain lighting situation and film speed. Light meters are also used in the fields of cinematography and scenic design in order to determine the optimal light level for a scene. They are used in the general field of lighting, where they can help to reduce the amount of waste light used in the home, light pollution outdoors, and plant growing to ensure proper light levels. Place a light meter out in front of you or have a friend hold it at the distance of the subject of the photo. Aim the sensor of the light meter at the camera. Hold the button on the side of the light meter down. Fire the flash on the camera. The meter will evaluate the degree of light from the flash and determine the correct aperture and shutter speed for the subject. Select the appropriate settings on the camera. The meter supplied you with the aperture and shutter speed recordings for correct exposure of the photograph based on the light at the location of the subject. Input these numbers into your camera. Exposure compensation. Even though the light meter in your camera is pretty sophisticated, sometimes it can get it wrong, especially with harsh contrasts or highly reflective surfaces. Changing metering modes may help this, but a more controlled approach is to use exposure compensation. Snowy mountains without exposure compensation. The same place with exposure compensation. Examples. Scenario 1. Sports. High speed is needed to freeze action. Use shutter priority. Set shutter speed to 1/800th of a second. The light meter sets the aperture to f10. If underexposed, change ISO to compensate, ISO 400. Scenario 2. Portrait. An artistic narrow depth of field is desired. Use aperture priority. Set aperture to f5.6. The light meter sets the shutter to 160th of a second. If underexposed, change ISO to compensate, ISO 100. Scenario 3. Night scenery. Ambient light is too low to accurately meter. Use full manual. Set aperture to suit scene, erring to wider f11. Set a long shutter speed to light meter's best guess, 20 seconds. Set ISO to lowest possible for correct exposure, ISO 100. Take a test shot and adjust settings if the light meter got it wrong. Exposure equation. Equation explanations. For reflected light meters, camera settings are related to ISO speed and subject luminance by the reflected light exposure equation. N squared by T equals LS by K, where N is the relative aperture, F number, T is the exposure time, shutter speed in seconds, L is the average scene luminance, S is the ISO arithmetic speed, K is the reflected light meter calibration constant. For incident light meters, camera settings are related to ISO speed and subject luminance by the incident light exposure equation. N squared by T equals ES by C, where E is the luminance, C is the incident light meter calibration constant. Illumination. Use in illumination. Light meters or light detectors are also used in illumination. Their purpose is to measure the illumination level in the interior and to switch off or reduce the output level of luminaries. This can greatly reduce the energy burden of the building by significantly increasing the efficiency of its lighting system. It is therefore recommended to use light meters in lighting systems, especially in rooms where one cannot expect users to pay attention to manually switching off the lights. Automatic cameras. Automatic cameras are highly trustworthy and can produce consistently good results as long as you understand them. The problem is that automatic cameras are easily fooled. If there is also a fool trying to use it, results become highly variable. The cameras have little intelligence, relying for that upon the user. Color. Infrared film. In infrared photography, the film or image sensor used is sensitive to infrared light. The part of the spectrum used is referred to as near infrared to distinguish it from far infrared, which is the domain of thermal imaging. Wavelengths used for photography range from about 700 nm to about 900 nm. Conclusion. In this chapter, we have covered the following in detail. Conventional aerial photography, small format aerial photography, chemistry of film exposure, the nature of light, the electromagnetic spectrum, rectilinear propagation, specular, diffuse and total reflection, reflection and absorption, wavelength and color, temperature. The human eye, morphology, rods and cones, acuity and circle of confusion, persistence of vision, parallax and perspective, photography versus the human eye. Film stock and processing, photochemical spectrum, structure and antihalation, speed and exposure, processing, densitometry, sensitometry, contrast control, gamma, controls of exposure, light meters and automatic cameras, color infrared film.